Swayam Prabha. Digital India. Educated India.
Friends, welcome to Earth Pressures Theories Part 1. Having studied the shear strength of soils, now we need to extend our knowledge in arriving at earth pressures, particularly on the retaining structures. So, in this lecture, we will be introducing the lateral earth pressure concepts, why we are required to study and where these lateral earth pressures are applied. So, in the coming to the introduction, the first rigorous analysis of the problem of lateral earth pressures was published by Coulomb in 1776. The first rigorous analysis of the problem of lateral earth pressures was published by Coulomb in 1776. Coulomb's theories were subsequently studied and supported by Rankine in 1857. Further, it was studied and validated by Tarjagi in 1934. These lateral earth pressures, mainly for structures like anchored bulkheads, retaining walls and other structures that resist earth movement, are in use since pre-Roman times. So, the necessity, the pre-Roman times, these retaining walls have been constructed. So, because of this, in 1776 itself, Coulomb has concentrated in evaluating and understanding the lateral earth pressure behavior, and when the walls are subjected to these pressures, and it has been studied and established. So, in 1857, Rankine validated Coulomb's theories, and further work has been produced. So, in this particularly in the earth pressure theories, we will be first studying Rankine's earth pressure theories, then we will be extending to Coulomb's theories, and then different graphical methods for computing lateral earth pressures on the walls. So, this leads to the determination of the lateral earth pressures coming when the retaining structures are subjected to movement. So, the amount of lateral earth pressures depending upon whether wall is having any movement or no movement, or whether if it is having movement, if it is away from the fill or towards the fill. So, lateral forces most typically develop against structures from the presence of soil or water against vertical sections. So, these lateral forces are basically developed against vertical sections. They basically due to present soil or water alone or water along with the soil. So, lateral forces most typically developed against structures from the presence of soil or water against vertical sections. Retaining walls and foundation walls are representative of structures to support an adjacent mass of the earth, while dams are used to retain bodies of water. So, the large bodies of water are retained by earth dams or dams. So, you need to calculate these pressures exerted by the bodies of water on the earthen dam sections and all. So, this knowledge on the lateral earth pressures is required. So, retaining walls and foundation walls, basically for the basement walls of the multi-story buildings, are representative of the structures to support an adjacent mass of the earth, because when we consider when we study in shear strength, we understood that one angle called angle of repose, and that is the maximum angle at which the soil can withstand without any support. So, that means that if you wanted to, many times situations arise that you need to maintain a vertical support. So, that means that you have to retain the soil to prevent it again from the reaching that angle of repose. Anything angle which is steeper than that angle of repose, the soil tends to settle to that angle. So, if you want a steeper support, a steeper section, then you need to support this particular soil again is by using sections like retaining walls or basement walls in the form of foundation walls. So where do you come across this thing? For example, you have got a building and the basement wall and which is located, and suppose if the building is having a drain and water is entering the drain. So in the process what happens is that you got a possibility of the accumulation of the water if there is inadequate drainage, or if the soil is not able to drain the water rapidly, then what happens is that there is accumulation of the water surrounding the basement wall. So this results in pressure like which is highlighted here, it shows and then causes the distress to the walls. So this the one which is resulted because of the soil as well as the water which is exerted, and that causes lateral earth pressure onto the soil, onto the wall section. So why to know about this means the reason actually is depicted schematically here from academic point of view, where the water drain which is shown here and where the accumulation of the water and it results in the settling backfill, and where the water pressure exerted on the wall. So the results in the distress in the basement wall section resulting due to the additional pressure which was not designed for. So in view of the above, it causes damage, and the aesthetic look of the basement or any interiors can get spoiled and then can endanger the safety of the building. In geotechnical engineering, it is often necessary to prevent soil movements. Like we said, if you have got a material which is settling at angle of repose, we can't afford always to have materials with slopes with angle of repose, and many times we require to retain the soil for to meet the public demand or utilities. So in such situations we need to resort for some structures like a cantilever retaining wall which is shown here, a wall section and then a surrounding soil. So here this particular soil is supported by laterally by a wall section which is there. So in order to design these particular wall sections against failure, against design point of view, you are required to know the lateral forces exerted per meter length of the wall. So the most of these structures which are particularly this cantilever retaining wall, all these structures, they are called plane strain structures because they are basically the other direction, they have a per meter length, the section which remains there. So the activity which remains in x and y direction, if x happens to be along this direction and y in this x happens in this direction and y in this direction, and the perpendicular to that z direction is supposed to be. So in this particular type of structures, the long structures, they are called plane strain structures. So here in the second diagram where is shown a braced excavation. See, you can do the excavation without any support up to certain depth. So beyond that you are required to support with shutters, and then these have to be braced with the tie rods. So what you see here, this particular section is again shows a braced excavation, a typical braced excavation where the pressures have to be resisted by this shutter, and then this is again force is transferred by these tie rods as compression members. And here what you see is anchored sheet pile wall where you have got the earth which is retained by a flexible structure called steel section, and that is anchored by a anchor which is at a certain location. So the location of the anchor and the forces which are coming onto the anchor, and then the forces which are coming onto the sheet pile wall, all these things in order to design this particular type of structures in geotechnical engineering, it is often necessary to prevent soil movements, and also in addition to that, in order to design these things, we need to understand these lateral earth pressures which can be generated because of the complicated conditions in combination with the different loadings which can exist. So further, a simple structures which are shown, we need to estimate lateral earth pressure acting on these structures and to be able to design them. So in the previous slide and in this slide, the structures which are shown, we need to estimate the lateral earth pressure and then we need to design them. So in order to do that, we need to understand about the theories behind this particular topic. So that's what we are for, and we are applying our knowledge of shear strength to this to understand about this particular lateral earth pressure theories. So here what we see, a typical gravity retaining wall. So, all its retaining capacity is derived from its own self weight, and here you see a fill. So, in this case any soil which is behind that wall and which is referred herein as backfill, the wall the fill material which is behind the wall referred herein as backfill material. So, here what you see is that a geotextile reinforced slope and reinforced soil wall, because in the urban areas and because of the paucity of the availability of the land, scarcity of the land, these structures are becoming quite common, and to meeting the demands economically as well as in a rapid savings in the cost of the project and all. So, the geotextile reinforced slopes and reinforced soil wall have got a particular prominence in understanding this designing the lateral earth pressure, extension of this, and able to design them economically, so that they can support these pressures which are exerted by the moving soil mass. So, in this slide what we are intended to learn is the typical retaining structures which can be possible, like the one which is shown is a plane form, where you can have a wall with vertical face and a foundation for this, and a battered back. So, the wall face can be battered this side, a battered face. So, a battered back or battered face and a stepped face. So, you have got a plane face here and then a stepped face towards exposed side and a stepped back. So, these are the different types of retaining structures. Otherwise, you have got a L shaped retaining wall or a T shaped retaining wall. So, this is referred as a cantilever retaining wall, or in order to have more sliding resistance, sometimes it is required at the base to provision of shear key. So, this is L shaped retaining wall with extension for shear key to have adequate factor of safety against sliding. And this is a buttress. So, this is the walls are particular wall section is buttressed at a certain interval on the exterior side, and a counterfort that is which is inside the fill. So, in this slide what we have seen is that a typical retaining structures, they can be in a plane form, and a face can be battered back or battered face, stepped face or stepped back. Mostly these are quite common, battered back and battered face, and then these T shaped retaining walls are sometimes with shear key, and sometimes when you wanted to have adequate resistance against the lateral pressure, it is ought to require buttressing. So, that is actually buttressing and counterfort retaining walls. In this slide some typical retaining structures which may come across for the basement walls, that is the constructed in open or shored excavation. That means that you will be excavating for certain depth to construct the basement. So, the material will be removed, and then these lateral forces are exerted onto these basement walls. So, in this case it is possible that these things can exert lateral forces, and here embedded walls constructed prior to excavation. Here what you see a vertical cross section, and then this supported propped here, and here this vertical wall which is supported with anchors. Then here we have got a different types of retaining structures. Sometimes you have got a diaphragm walls of concrete diaphragm wall panels. So, a panel type excavations are done, and then they are constructed. Basically they are done for offshore structures. And contiguous board wall, this particular wall section is that you will be driving the piles as very close spacing, and then they are connected. And here the secant board wall is that almost these piles are constructed without any gap and then covered. So, this actually forms as a retaining structure. So, here you have another bridge abutments. Basically, when you have got bridges constructing, then you have got abutments which are coming. The soil area has to be supported when the bridge is commencing. And similarly the bridge at the commencement as well as bridge at the end. So, you require abutments. So, here again you have a T-shaped bridge abutment where you have got a girder sitting here, and then in case if the soil is adequately not having adequate bearing capacity, then you have got piled bridge abutment, and in this case embedded cantilever where that the section will be embedded within the soil and then which is supported. And now that recent trend is to adopt cost economic construction, or to have to construction with the reinforced earth technology, where the reinforced earth abutments are becoming popular. They are gaining momentum because of their savings and cost economics and aesthetic look which can give from by adopting this technology. Then other technique which is coming is called gabion wall technology, where you have got the locally available material like stones or rounded aggregates there which are cannot be used for any construction, can be adopted for use in this here, and then can form a gabion walls. That means that a prefabricated meshes will come and then they will be filled with these rounded aggregates, because these aggregates which are not good for construction can be used here, and then in addition to that, these gabion walls can act like a semi gravity retaining structures and also have a good retaining characteristics as well as some good drainage characteristics, and also is with the locally available materials it is possibility of having a good aesthetics. And the another technique which is actually having is crib wall construction. In some areas is very popular. So these are the different what we are trying to learn is that the need for in order to, before learning about the earth pressure theories, we are trying to understand about different typical retaining structures which are available in different areas, like in the basement walls or bridge apartments, in for example in the hilly areas when you have got a cutting in a railway, or when you need to be supported, and then in that case this depending upon the specific situation, depending upon the properties of the soil and other details, will be able to adopt this particular structure. So here in this slide a typical gabion wall is shown. Here what you see is this material is arranged in a fashion like this. So these are the different cages and filled here, and this particular slope height which is there behind and is retained by using this. So this is a in a sense it is very rapid and is possible to construct rapidly, and then also use the locally available materials where the abundant availability of the stones which are there, so they can be adopted for usage here in the construction. This is a typical contiguous board pile wall. What you see is that typically board piles have been driven and then they are attached to a beam. So what you can see is that a typical contiguous board pile wall in this picture. So it's shown from the academic point of view for giving you an idea about how the contiguous board pile wall look like. Here for a basement for a building, you can see a soil or a surrounding area is protected by using another technique called soil nailing technique, or this particular technique is generally used for temporary protection or sometimes for protection, where in this case again the lateral earth pressures again countered by the nails which are embedded within the ground, and they actually take these lateral forces because of the soil nail interaction, and in the process the nail gets a tension which actually resists this lateral movement. So here what you see is that a facing, and then these are the connections or end connections for the nails, and this is the basement which is coming up. So these are the typical soil nail low slope which is shown for a basement excavations. Otherwise, if this slope is not supported, so there is a danger of failure. So this is a typical crib wall which is shown here, because these crib walls they look like a open mesh type here, and with headers and stretchers which are running like this, and they have a good interlocking characteristics. And what need to do is that this entire fill material filled with soil here. So because this crib wall is having good aesthetics, that is one merit of this particular construction, and good drainage and allow the plant growth. So where you have got environmental friendly aesthetic appearance which can mingle with the surrounding environment very easily. So this is a typical crib wall where your possibility of the interlock is created by these headers and stretchers which extended into the soil, and then the soil will be filled in these gaps, so that they have the confinement which is actually required, and because of that it actually takes that lateral earth pressures which are exerted onto the wall. So before introducing, so let us look whether water can exert pressures or not. So here a pool of water which is shown here in a typical swimming pool. So here the vertical stress and the horizontal stress is same, in the sense what will happen is that the sigma V or sigma H which is acting is same, because the pressure is same in all directions. And another thing is that water is actually not having shear strength. So, because of that horizontal stress is equal to vertical stress. So, the ratio sigma h by sigma v is equal to 1 for water. So, if a vertical column of water is there, then it has got lateral pressure which is exerted, and that is the stresses are equal in all direction. Why? So, that is answered because it has no shear strength. Contrary to that, if you look now earth and water pressures, if you look, let us consider that a T-shaped retaining wall is retaining a water. So, in this case here, because of the concept which is introduced, the total hydrostatic pressure is given by sigma E is equal to sigma V is equal to sigma H, because the vertical direction and horizontal direction. Here the vertical direction pressure is also shown as lateral direction, because sigma V is equal to sigma H. So, because H is the height of the wall and the H is the height of the water which is retained with a unit weight gamma W. So, with that what will happen is that sigma V is equal to sigma H is equal to gamma WH is the pressure at this particular point. So, the net force which is exerted on the wall, if you look into it, so H is the height, gamma WH is the ordinate here. So, it is nothing but half gamma WH square is acting per meter length of this wall. Suppose if the water if this length of the wall is say 10 meters, then the 10 meters length or this much total force is going to act laterally. Sometimes you consider now this is a level which is indicated, and then there is a soil which is gamma bulk having a moist soil and no water. In this case, the vertical pressure sigma V is again indicated by gamma B H, where gamma B is nothing but the bulk unit weight of soil and H is the height of this thing. That is because this stress is obtained. This is a vertical stress. Though it is a vertical stress, it does not indicate the direction of the stress. This is the vertical stress is also indicated. The lateral direction which is shown in the figure does not indicate the direction of the stress, is actually acting in the vertical direction. That means that the vertical stress at this point is 0 and vertical stress at this point is gamma B times H. This is a total vertical pressure. Now, let us assume that both soil and water and they are there at the top of the wall. That means that the water level is up till here and the soil level is up till here, and H is the height of the wall. In this case, the sigma V is equal to total stress is equal to sigma V is equal to gamma sat H, because the soil is completely saturated with water. So, the saturated unit weight of the soil is gamma sat H. So, the vertical stress is sigma V is equal to gamma sat H, and because of the presence of the water and all voids are connected with water. So, the pore water pressure U is equal to gamma WH, the pore water pressure is equal to U is equal to gamma WH. So, the effective stress is nothing but sigma V dash, effective vertical stress or effective vertical pressure, which is nothing but gamma sat H minus gamma WH at a depth of H from the top surface is sigma V dash is nothing but gamma dash H. This effective vertical pressure is indicated by sigma V dash or sigma V bar. So, wherein you have these are referred as the total stress minus pore water pressure. So, in this case the effective vertical pressure sigma V dash is equal to gamma dash H is given in this case. In soil, now let us consider the soil being stratified. You have got soil 1, soil 2 and soil 3. So, they are subjected to self weight. So, these conditions when that surface is horizontal, so these stresses which we discussed earlier, and they cause geostatic stresses, and these are geostatic vertical stress and geostatic horizontal stress. The magnitude of this horizontal stress depending upon the stress history of soil. If the soil is normally consolidated, then the magnitude of the stress sometimes is less, and if the soil is more consolidated, then there is the possibility of the locking of the stresses. In such situations, there may be a large horizontal stresses which can be possible. So, in this case, a vertical stress and horizontal stress, and in soil, contrary to the water, in water we have seen that being no shear strength, sigma V is equal to sigma H, but in this case sigma V is equal to not equal to sigma H. So, horizontal stress is not equal to vertical stress, because stresses are not equal in all direction soils. So, previously in water we have seen that they are equal, but in this case they are different. The reason is again the soil possesses shear strength. So because of that, what we have is that in soil you have got a different vertical stresses and horizontal stresses, and this apportioning this, what component of horizontal stress is, that depends upon the several factors like the type of material, the type of deposition, and the way it is the stress history which was lying at a particular area, and that can dictate this combination. So this lateral earth pressure, when we wanted to introduce, the effective lateral earth pressures are determined by transferring a portion of the effective vertical pressure. So that's what has been discussed now. Effective lateral earth pressures are determined by transferring a portion of the effective vertical pressure. That means that effective lateral earth pressures are determined by transferring a portion of the effective vertical pressure. This amount of transfer, that means that this is found to be depending upon the type and unit weight and the strength of the soil behind the wall, and the direction and amount of the wall movement, So the type and unit weight of the and the strength of the soil, and soil behind the wall, and the direction and amount of the wall movement. The amount of transfer is expressed in terms of a coefficient called lateral earth pressure coefficient. The amount of transfer is expressed in terms of a lateral earth pressure coefficient called K. So lateral earth pressure coefficient can only be applied to effective vertical pressures. As we just now seen that when you have got a water pressure, then the lateral earth pressure coefficient is K is equal to 1. Whereas in case of soil, because of its shear strength characteristics, possessing shear strength characteristics, the lateral earth pressure is not equal to lateral earth pressure in the vertical direction. So lateral earth pressure is not equal to the vertical pressure. So the amount of transfer is expressed in terms of a lateral earth pressure coefficient K, where K is equal to sigma H dash by sigma V dash, where sigma H dash is the effective horizontal pressure, sigma V dash is the effective vertical pressure, and K, in many the notations are there, K, K naught, even in this lecture also you will see K, K naught or K areas, the notations, but it is nothing but a lateral earth pressure coefficient at rest, it is called. So lateral earth pressure coefficients can only be applied to effective vertical pressures, because the water cannot have this particular pressure. So the coefficient of pressure at rest for coefficient of lateral earth pressure coefficient is equal to 1 for case when the water is exerting a lateral pressure. So they cannot be applied to total pressures, because the total pressure has the component of effective stress and component of water pressure. So when you have this component of water pressure is acting, that means that you cannot actually apply a coefficient, lateral pressure coefficient to the water. So these lateral earth pressure coefficients can only be applied to, this is always a misunderstood concept, so it has to be, students have to be noted that lateral earth pressure coefficient can only be applied to effective vertical pressures. So let us consider a case where you have got the previous case, we have considered a T-shaped retaining wall or a cantilever retaining wall is having a backfill which is saturated, and it is filled with, it is having a water level up to the brim of the wall, that is at the top surface of the ground. So in this case, the horizontal effective earth pressure is nothing but sigma H dash is equal to K times gamma dash H, because here the gamma sat minus gamma W, that is the water pressure, has been taken out. So what you have is that sigma H dash horizontal effective pressure is equal to K times gamma dash H, because this gamma dash H is the vertical stress component. Now what we have done is that by using K is equal to sigma H by sigma V or sigma H dash by sigma V dash. So what we have tried to find out is that K times gamma dash H is nothing but the lateral component. So sigma H dash is equal to K gamma dash H, and the pore water pressure is equal to U gamma WH. So in case if you wanted to express that in the total earth pressure, lateral earth pressure, then it has to be calculated as sigma H dash is equal to K gamma dash H plus gamma WH. So K gamma dash H plus gamma WH. So if you note here, the gamma WH, though it is a lateral pressure which is acting, but it does not carry any coefficient. So here in case of total pressure, what we have is that sigma H dash is equal to K gamma dash H. So the lateral pressure coefficient is only applied to the effective vertical effective horizontal stress, which is here in this case the effective vertical stress, that is gamma dash H into K plus gamma WH. So this is a deliberation what we discussed for lateral pressures in saturated backfill. So when we come to this now, there are many areas that theories which have been postulated. The Rankine first assumed that a wall or in a vertical section is assumed to be uniformly is assumed to be non-yielding type. That means that a section is a vertical section is assumed to be remain in position, non-yielding type, in the sense that no strain at all in the direction, no movement at all. That is one case. Then there may be possibility that entire wall section moves away from the backfill parallelly. So that is one type of possibility. And another type of possibility is that one type of wall section can move towards the, that is, the wall section can move towards the backfill. So the categories of lateral earth pressure have been quantified. Like in case if you have got a normally consoled clay and which is only having has undergone the, no longer is undergoing any consolidation, in such situations there may not be any lateral earth pressures. That means that they may be a non-yielding type. In such situation, the coefficient of lateral earth pressure conditions like non-yielding type can apply. But if there are cases that where the chances of movement of the vertical section away from the backfill or towards the backfill, then apportioning of that is actually depends upon this particular theories. So this was actually first postulated by Coulomb and then it was refined by Rankine. So in the Rankine's theory, we will be discussing about the Rankine's theory and the assumptions in the next lecture, but here before that we will be understanding more about the non-yielding type and we will try to correct which is required from the shear strength point of view. So here this case many times the parallel sections which are entire movement of the wall which may not be possible. So in this case a typical T-shaped retaining wall or a cantilever retaining wall was selected, and this particular section which shows a at rest case where no movement situation, and in this case which is postulated and named by Rankine as active case, where the wall tips or moves away from the soil. So in when the wall actually moves away from the soil, and this condition is called active case, and the pressure or lateral earth pressure which is computed in that case is actually called as active earth pressure. And if there is a case that the wall moves into the soil, like it can happen in situations like in bridge abutments where the wall can move into the soil, so there is actually possibility of passive case. Or if you have got a retaining wall and there is a fill which is in front, and when the wall is actually moving away from the backfill, at the bottom portion or the downstream portion, the soil in front of it can be subjected to passive case, because in the bottom portion the soil will be moving towards the fill. So that at that point that actually becomes like a backfill and then exerts a compressive forces into the soil. So here what happens is that these three cases which are states which are mentioned here called active case, at rest case and passive case. So mostly so in this case at rest case where that no movement condition or zero strain condition which is called, and that particular condition and then particular pressure at pressure the coefficient determined at that condition, a zero strain condition, is called coefficient of earth pressure at rest, that is called zero strain condition. So the soil strength and state of the stress in a soil mass during the wall movement. So consider an isolated element in a typical backfill without any movement or strains in the soil mass. So let us assume that you have got a cross section of a retaining wall. So figure above shows an element with the principal effective stresses acting on it. So here what you see, a vertical cross section of a wall, h is the height and this is the backfill, with the gamma m is the gamma moist, is the backfill unit weight, and this is the element under consideration. Sigma v dash is the vertical principal stress, because it is called principal stress because no movement conditions, there is no shear stress. So the shearless planes are called principal planes. So in this case they happen to be, so this is the horizontal plane and this is one principal plane where the shear is 0. So sigma v dash, so this is the major principal stress, and sigma h dash, sigma v dash which is vertical principal stress acting on the horizontal plane, and this is the vertical plane is again a shearless plane. Then sigma h dash is the horizontal effective pressure. So, sigma h dash is equal to k sigma v, where k is the lateral earth pressure coefficient, k is equal to k naught, which is written here. So, sigma h dash is the effective horizontal pressure and k is the lateral earth pressure coefficient, sigma v is the lateral earth pressure, sigma v is the effective vertical pressure. So, this particular figure shows an element cross section, element with subjected to vertical effective pressures and horizontal effective pressures. The sigma h dash is equal to k times sigma v. Now, if the wall is allowed to deflect away from the backfill and develop some strain. So, in this slide what we have shown is that if the wall is allowed to move like this, which is shown typically, and deflect away from the backfill and develop some strain in the soil mass, the element undergoes some strain. So, that is actually represented systematically in triaxial test. We call in the triaxial test, these major vertical these principal stresses are simulated, vertical principal stress and horizontal principal stress are simulated in a similar way, and by holding the horizontal principal stress, the sigma h dash, and increasing the sigma v dash, the failure is induced the way it is shown here. So, here alpha is the failure plane, which is shown here, the possible failure plane, and with a deflection because of the lateral strain in this direction develops. So, here what happens is that the sigma h dash and which is the horizontal effective stress, sigma v dash is the vertical effective stress. So, this tau alpha is the shear stress along this plane, and then the sigma alpha is the normal stress which is acting here. So, shear stress tau alpha and normal stress sigma alpha, which act on potentially developing shear plane and angle alpha from the. So, this is a potential failure plane which is shown here. So, the shear plane behind development behind a wall yielding away from the backfill is shown. So, when the wall yields away from the backfill, there is a possibility of a shear plane development. So, if the wall is allowed to deflect away from the backfill and develop some strain in the soil mass, the element also undergoes some strain. So, here what is been shown is that along this failure plane, these stresses are simulated. So, these conditions are simulated experimentally to arrive at this strength properties tau alpha and that stress conditions along that failure plane, that at failure. If they reach to the failure, then they tend to give the failure, and then we are able to determine the properties. So, let us look into this soil shear strength and state of stress in a soil mass during the wall movement. So, here in this slide what we have taken is the a particular element, and then when it is subjected to the stress conditions when it is subjected to a movement away from the backfill. So, these conditions can be simulated in a triaxial or a direct shear test, where the strain is induced. This may be shear strain in case of a direct shear box, or it can be by holding a constant sigma h, you can increase the vertical stress. So, that is nothing but a deviated stress in case of a triaxial test. So, moment it reaches this tau f, it can reach to the failure. So, these as a gradually when it actually getting strained, some possibility of reaching the tau f, and then a failure of a specimen can take place. So, that is actually shown a typical stress strain relationship here, and this element which was shown in the previous slide is shown here, is in exaggerated and shown. So, this epsilon, which is actually is nothing but delta hs by hs, that is the vertical strain. So, here these conditions are simulated by applying the vertical deviated stress, so that these conditions, failure conditions are simulated. So, k is equal to sigma h dash by sigma v dash, or sigma h bar by sigma v bar, when alpha is equal to 45 plus 5 bar by 2. So, more details, these details you would have already acquainted yourself while looking into the shear strength aspects of soil. So, here like this, when you do the number of samples like with the different horizontal stresses, then we get the different Mohr circles. So, this particular component which is called Mohr circle, where we represent these conditions in a Mohr circle formation. So, you can see here this is for another combination of stresses. So, you have got a sigma h1, then the response is here sigma h2 and a sigma h3. So, if you are able to join these all these Mohr circles, then you get the envelope, and that envelope is called the shear strength envelope. And here this is the equation of this envelope lies like tau alpha is equal to sigma alpha tan phi plus c bar. So, c bar is that intercept here, and that is called cohesion, and this inclination of this shear strength envelope is called the angle of internal friction. So, the C bar and the phi bar, and if they happen to be under consolidated drained conditions, or if you have got if you are referring as a drained parameters, they are called C dash or phi dash, that is the drained parameters or the drained strength parameters of the soil. So, in case if the bore pressure drainage is not allowed, and for example, in case of a consolidated undrained conditions also, then you get that is in case say unconsolidated undrained test, you will get the undrained conditions. So, here when whatever the element we have seen, and if it is a granular soil and if it is a normally consolidated soil, then the shear strength envelope which is runs like this, where C is equal to 0. In such situations, the envelope lies there, and if these conditions, like if it is if this circle, if it is not touching this particular envelope, that means that it is not yet reached the failure. So, in this case here, this tau alpha, sigma alpha, they are the stresses, that is the shear stress conditions that which are available here, tau alpha and sigma alpha, and which are actually less than that shear stress which is actually failure shear stress. So, in that case the failure is actually not attained. The moment it touches this failure envelope, that means that we can say that the failure is attained to the soil. So, the more stress conditions shown on the more strength diagram, where here this is the shear strength envelope. So, as far as this thing is concerned, the sample is said to be stable. So, the stress circle is not at a strength circle, since the tau alpha has not yet reached the maximum value before failure. So, the tau alpha is not yet reached the maximum value before failure. So, here what you can see is that the stress circle which is represented. So, this circle will become the more strength circle moment it becomes tangential to this envelope. So, this is actually when you do not have this envelope, in order to construct that, you need to have test this sample at different horizontal pressures and create number of more strength circles, and by drawing a tangential line to this more circles, the more strength circle will be able to generate an envelope, and that envelope is actually resulting as a shear strength envelope. Here if you know the properties of a soil, and here in this case a phi dash, which is C dash is equal to 0 and phi dash, and in this case where we can say that the stress circle is not at a strength circle, since the tau alpha is not yet reached maximum value before failure. So, returning wall movements and related state of stress, if you look into it, where we are actually discussing about the K naught state, where that is at rest condition, where the no movement arises, and when the minimum there is deflection away from the backfill can create and the pressure will be minimum, that is Ka is called active earth pressure conditions, when it actually moves away from the fill. And then when the wall moves towards the fill, that is deflection towards the backfill, then there is a Kp which is actually maximum. So, the coefficient Ka is minimum when it is actually moving away from the backfill, and Kp is maximum when it is actually moving towards the backfill. So, apportioning of that will be depending upon the surrounding soil properties and other conditions which we will be discussing. The possible wall deflection and related range of the lateral earth pressure coefficients are shown here, where you have got that is at rest conditions or no yielding conditions. The zero strain condition is called K naught condition, is called coefficient of earth pressure at rest conditions. So, non-yielding walls at rest condition, let us consider the non-yielding walls at rest condition. At rest conditions is defined as a zero of lateral, a state of zero of lateral yielding, and there is no lateral strain, that is epsilon is equal to 0. At rest condition is defined as a state of zero lateral yielding and there is no lateral strain. That means that you have got a typical cantilever wall, and you have got sigma V dash and sigma H dash, where epsilon is equal to 0. So, K naught is equal to sigma H dash by sigma V dash. So, here the sigma H dash is the horizontal effective stress at rest condition, that is because of the K times or K naught times the vertical effective stress, where in this case the epsilon is equal to 0, that is actually the wall is at rest backfill, that is non-yielding type. So, if this typical at rest stresses on most in the diagram, if you represent for a normally consolidated soil, means that a soil that has not been loaded by greater stresses than its own weight and is no longer consolidating from its own weight. That means that a normally consolidated soil or a soil that has not been loaded by greater stresses than its own weight and is no longer consolidating from its own weight. So, in such situations the envelope which is in tau and sigma space can be represented like this. This is the shear strength envelope which is phi with its friction angle is phi dash, and at rest condition if you have k naught is equal to horizontal effective stress at rest condition, that is sigma h naught bar divided by sigma v bar, which is the vertical effective pressure. So, in this case this is this condition, if you represent this particular condition, that is this is on the shearless planes. So, this becomes the this becomes the sigma v becomes the major principal stress is the principal plane here, and this is the vertical plane. This vertical plane is again another principal plane which is acting, that is sigma h naught bar. So, here the sigma h naught bar is equal to nothing but k naught into sigma v bar. So, that is nothing but the k naught. So, this k naught value, coefficient of pressure rest value, depends upon the several other factors like the relative density of the soil and the stress history and other type of loading and all. So, that we will be discussing, but here this particular condition like can be simulated like if you prepare a direct shear test, and if you apply say a vertical stress, a normal stress to the soil sample, and say the test is not yet commenced. So, let us assume that you applied 100 kN per meter vertical stress, and let us assume that this particular value of this k value is about 0.5. In that case, this particular case, this particular condition which is referred there is again at rest conditions. That means that if that particular material under test is having say phi dash, then if you draw a the at rest circle or at rest stress circle, and that comes out something like this, where you have got a circle and which is actually far away from the failure envelope, that is the shear stress envelope. So, even in the direct shear test at the initial conditions to some extent can represent this particular case like at rest conditions what we are seeing in this slide. In the earth pressure at rest, in estimating we have some assumptions like cohesionless soil and a state of elastic equilibrium prevails in all case. That means that we assume that the elastic equilibrium conditions, and no external loading and stresses are only due to gravity only. That means that only geostatic conditions, and no lateral strains, that means the lateral strains are 0, no permanent deformations in the lateral directions, no permanent deformations in the lateral. Importantly, at k naught strains there are no lateral strains. So, one important thing is that at k naught state there are no lateral strains. So, coefficient of earth pressure at rest can be determined at a particular depth. Say if this happens to be like sigma v dash and sigma h dash, and if this at a particular depth z at a point which is shown there, then coefficient of earth pressure k naught is equal to sigma h by sigma v. So, soil deforms under its own self weight, but it is prevented from deforming laterally because of its infinite extent in lateral directions. So, at a particular point of this dot, if you take, the soil deforms under its own weight, but it is prevented from deforming laterally because of its infinite extent in all directions. So, from using the theory of elasticity fundamentals, if you write the lateral strain epsilon is equal to sigma h by E, assuming that Hooke's law is valid, sigma h by E, where E is the modulus of elasticity of the material soil, that is minus mu into sigma v by E plus sigma h by E is equal to 0. So, where mu is the Poisson's ratio and sigma v is the vertical stress and sigma h is the horizontal stress. So, by simplifying this, because the lateral strain is 0 in k naught state, when the wall is non-yielding type, then sigma h by sigma v, by simplifying this, it results like sigma h by sigma v is equal to mu by 1 minus u. So, sigma h by sigma v is related with Poisson's ratio, which is mu by 1 minus mu. In a normally conserved soil deposit, the vertical principal stress is equal to the weight of the overburden. So, that means that in a normally consolid soil deposit, the over consolidation ratio will be equal to 1. So, with that we can write sigma v is equal to gamma z, and sigma h now, because in the previous slide we have derived sigma h by sigma v is equal to mu by 1 minus mu. So, what we do is that sigma h is equal to mu by 1 minus mu into gamma z. So, with that we can write sigma h is equal to k naught gamma z, and k naught is equal to, we have substituted now is mu by 1 minus mu. So, sigma h is equal to mu by 1 minus mu into gamma z. The total resultant pressure which is acting P naught is equal to half K naught gamma z square, where K naught is the earth pressure at rest, that is mu by 1 minus mu. So, the linear distribution of the earth pressure at rest is shown here as a triangle, 0 at the top like vertical stress, and K naught gamma z which is at the ordinate at this particular point. So, P naught which is the resultant is half K naught gamma z square. So, value of the K naught, that is coefficient of earth pressure at rest, depends upon the relative density of the sand, process by which the deposit was formed, and the stress history. So, the three factors which are required to be determined is that relative density of the sand and the process by which the deposit was formed and the stress history. So, for normally consolidated soils, it is common to use K naught is equal to 1 minus sin phi, or sometimes K is equal to 1 minus sin phi, and this is a well known deliberation this formula which was used and put forwarded by Jackie. So, after Jackie we can say that K naught is equal to 1 minus sin phi, where phi dash is the effective friction angle. For more consolidated clays like K naught is equal to 1 minus sin phi dash into OCR to the raised power sin phi dash. Sometimes the deliberations like many empirical expressions like K naught is equal to 1 minus sin phi dash OCR to the power of 0.5 is also in use, but for consolidated clays K naught is equal to 1 minus sin phi dash OCR, where OCR is the over consol ratio and sin phi dash to the raised to the power of sin phi dash, this is also in use. The K naught is of normally consolidated clays is related to the plasticity index also, and this was after alpha 1967, where K naught is equal to 0.19 plus 0.233 log to the base pi. So, with an increase in plasticity index, so that you can see that there will be a change in the value of the coefficient of earth pressure at rest K naught. So, effect of submergence, if you take gamma psi is equal to gamma sub into gamma dash. So, with that what we can get is that now the even with the conditions here now, because earth pressure ordinate now it becomes at rest is that K naught gamma dash z, K naught gamma dash z. So, with that what will happen is that P naught is equal to half K naught gamma dash z square. So, the lateral earth pressure when it comes to that we have now is half K naught gamma dash z square, that is P naught, plus Pw, that is because of the resultant pressure due to water, the pressure exerted by the water, when you are actually dealing about this this particular half K naught gamma dash z square plus half gamma W z square. So, in the next lecture, that is under earth pressure theories 2, what we do is that we will introduce to the Rankine's earth pressure theory, and then different cases which are actually governed under this particular theory will be discussed, and we will try to look into some problems and applications of that Rankine's theory and assumptions which are involved in that, and then which are connected to again by adopting the Morse circles, and how this in a tau sigma space, how these active conditions and passive condition can be simulated for a given material, can be cohesionless soil and cohesive soil can be discussed. So, in the next class we will be discussing about this Rankine's earth pressure theory. So, in this lecture what we tried to look into is that we introduced the earth pressure theories, and then the relevance for determination of the earth pressure, need for understanding the earth pressures, and we discussed in length about the earth pressure at rest, and where the non-yielding case maybe certain situations like we have got a normally consolidated soil as a backfill deposit, and where it is the case where which may not really exist, and that situations this possible for us to have at rest conditions. But the majority of the conditions where we have is that active conditions where you tend to design for active state. So, that we will be discussing in the next lecture.